어? 네, 한성민 씨 안녕하세요. 네, 정상목 씨 안녕하세요. 네, 박건우 씨 안녕하세요. 박건우 씨는 이제 그 격리가 해제되신 건가요? 아니면은 이제 오늘 저녁에 해제가 된다고 그러셨나요? 네네, 알겠습니다. 자, 혹시 질문 있으면 질문해 주시고요. 예, 질문이 없으시면 강의를 시작을 하도록 할게요. 오케이. 네네. 박근혜 씨 질문하시죠. 네. 뉴메리컬 솔루션을 계산하는 방법을 정확히 모르겠다고 하신 한성민 씨의 질문에서, 어, 뉴메리컬 솔루션 자체를, 그러니까, 트랜지언트한 웨이브 폼을 구하는 일까지는 하셨나요? 네. 시간에 따라 가지고 웨이브 폼을 만들어내는 것까지는 했나요? 네. 자, 그러면 이제 예를 들어서 우리가 y 파라미터를 구하고 있다라고 생각을 하면 이 y 파라미터라는 거는 볼티지 익사이테이션에 대해서 어, 이제 이런 거죠. 우리가 어떤 델타 V를 각 운동량 오메가로 넣었을 때 그걸 델타 I를 또 오메가로 이렇게 표시를 하면 되겠죠. 그래서 이거를 근데 여기 사실은 y 파라미터라는 거는 일반적인 케이스에 대해서는 다단자 소자일 테니까 이렇게 쓰긴 어려울 것 같고 y가 있으면 알파하고 베타라는 그 터미널 인덱스가 들어갈 수 있을 것 같아요. 그래서 이 뒤에 있는 녀석이 익사이테이션이 일어나는 터미널에 대한 그 터미널 인덱스가 되게 돼 있고 앞에 있는 것이 이제 요 관찰하는 터미널에 인덱스가 들어가게 돼 있습니다. 물론 지금은 여러분이 2단자 소자를 하고 있을 테니까 예를 들어서 여러분들이 명시적으로 계산하고 있는 건 사실은 뭐 어노드 이런 걸 계산을 하고 있겠죠. 어노드 쪽에 전압을 인가하고 어노드 쪽에 전류를 뭐 보고 있다든지 하게 될 텐데 이제 뭐 다양한 케이스들이 트랜지스터에서는 나타날 수가 있겠습니다. YDD라든지 YDG 같은 거라든지 혹은 YGG 이런 녀석들이 나타날 수가 있겠죠. 그래서 이런 것들이 나타날 수 있으니까 일반적으로는 저렇게 써야 될 텐데, 자, 지금 질문은 무엇이냐면 현재 이제 생각해 주신 게 델타 V를 시간에 대한 함수로 표시를 했을 때 이거를 예를 들어서 우리가 이렇게 사인 오메가 t에다 어떤 작은 앰플리튜드를 가지고 이렇게 만들어내는데 성공을 했다 칩시다. 그리고 나서 여러분들이 이걸 또 구해내는데 성공을 했어요. 그런데 여기서 말한 그렇게 해서 구했겠죠. 근데 지금 여러분들이 구해야 되는 이 y 파라미터라는 것은 사실 시간 영역에서 계산을 하는 것이 아니라 주파수 영역에서 계산을 해야 되니까 이 인풋과 이 아웃풋을 모두 다 주파수 영역에서 표시한 델타 V와 주파수 영역에서 표시한 델타 I로 만들어내야 된다 라는 게 필요하겠죠. 그래서 생각을 해보면 여러분들이 어떤 일이 생길 거냐면 요걸 구해보면 결국은 트랜지언트 이펙트들이 다 지나고 나면 이게 사인 오메가 t에 대한 어떤 개수가 하나가 나타날 거고, 그 다음에 코사인 오메가 t에 대한 그런 개수가 나타나게 될 거예요. 자, 그런데 여러분들이 다 아시겠지만 이렇게 우리가 코사인을 위주로 해가지고 바라볼 때 이게 만약에 A라고 해볼까요? 이게 B라고 해볼까요? 그러면은 얘네들을 그 주파수 영역에서 나타나게 되면 어떻게 되게 돼 있습니까? 사인에 해당하는 것은 J 델타 V가 될 거고요. 요 코사인 B 코사인 오메가 T 그 다음에 A 사인 오메가 T에 해당하는 것은 B 더하기 JA 뭐 이런 식으로 되겠죠. 네. 그래서 요것을 구하시면 요거라는 건 이것과 이것을 가지고 나눗셈 연산을 해주시면 그러면 복소수가 나타나게 될 겁니다. 사실 복소수가 나타난다고 하지만 이 경우에는 아주 단단한 것이 JA를 J 델타 B로 나눠준 거니까 델타 B는 어떤 실수가 되겠죠. 그래서 이제 마이너스 J를 양변에 곱해주게 되면 이렇게 나타날 거라는 걸 아실 수가 있습니다. 즉 무슨 얘기냐면 얻어지는 델타 I 중에서 사인 오메가 T하고 이렇게 결맞게 나타나는 녀석은 그 녀석의 앰플리튜드를 델타 V로 나눠준 것이 바로 Y 파라미터의 리얼 파트에 해당하는 것이고요. 그 다음에 코사인 항으로 나타나는 것은 그것의 마이너스를 취해 준 것이 그리고 그거를 델타 V로 나눠준 것이 Y 파라미터의 이미지너리 파트에 해당하게 될 거라는 겁니다. 무슨 얘기인지 이해가 되시죠? 그러니까 Y 파라미터가 실수면 사인을 넣었을 때 그냥 사인이 나오게 돼 있는 거고, 물론 코사인을 넣었을 때도 코사인이 나오게 돼 있는 거고요. 네, 그렇게 돼 있고 이미지너리 파트가 있었을 때는 저와 같이 사인과 코사인을 바꿔주는 일을 하게 된다는 겁니다. 따라서 여러분들이 하셔야 되는 것은 이 웨이브 폼이 나타나잖아요. 그러면 웨이브 폼은 분명히 일정한 주기를 가지고 있을 거고 그 주기는 바로 각속도, 각주파수인 그 오메가에 해당하는 어떤 주기를 가지고 있을 거예요. 그걸 바탕으로 해서 주기를 판단하시고 그 주기를 가지고 사인 성분의 앰플리튜드와 코사인 성분의 앰플리튜드를 취함으로써 A하고 B 코에피션트들을 구할 수가 있게 되고 이로부터 Y 파라미터를 구할 수가 있을 겁니다. 네. 질문에 답변이 됐나요, 한성민 씨? 그리고 박건우 씨도 비슷한 질문인 것 같은데요. Okay, so do you have any other questions? So if you have a question, please let me know. Then I will try to answer your question. And now let's go to lecture. Okay, so Mr. Jung, you have another question. Mm, in the double gate example, if you apply pulse signal to your gate, I guess. So if we go to higher and higher frequency, and your slope means that maybe the transition between your low voltage and high voltage, right? So in your question, so you just say this is slope. So anyway, this is a transition from low to high, and yes, so in this case we have different behavior. So of course this is only due to the capacitance. So double gate or any kind of MOSFET device has capacitance in it. So in order to make the operation of a MOSFET, we have to introduce oxide region. And if we go to a low frequency, then this capacitance can be negligible compared with the conductance of the channel. However, if we go to higher and higher frequency, then this component, the C component, contribute to the Y parameter in the form of this J omega C term. So let's say that this is a fixed constant calculated or generated by the gate capacitance, and if we increase our frequency, then now it can be comparable with our conductance, the real part of a Y parameter. Or if we go higher and higher case, yes, we will have further and further contribution from this imaginary part of Y parameter. Of course, please note that Y parameter, that is a small signal quantity. Small signal quantity. So it means that when we talk about Y parameter, we just assume that we have applied a certain bias voltage to gate and of course drain, and only change slightly its voltage value and measure the reaction of or response of our terminal current. However, in the same manner, if even when we consider large signal operation, so starting from 0 to VDD or starting from VDD to down to 0 volt, even in this case, it is true that if we go to higher and higher frequency, this capacitance really plays a critical role in determining this waveform. So you will actually find the delay of your output signal. Although you just make almost abrupt change in this part, your capacitance, your capacitor should be charged. So it will take a certain time. For example, let's think about this simple behavior. So if we just consider this system, yes, this is the source and this is drain and gate. Yes, so now you are increasing your gate voltage. So it now dictates that you have to collect more and more charges in order to make it to satisfy the gate voltage condition. So think about this one. If you are ramping your voltage quite slowly, then always your source and drain can provide the electrons into this channel region yes, almost immediately from the viewpoint of this time scale. But instead of that, now you are almost abruptly increasing your gate voltage. Of course, in this case, still this channel region require more electrons than before, so electrons should be provided from our source terminal and drain terminal. However, electrons are not just disappear here and just suddenly appear there. They should move. However, if we have certain finite time for our electrons travel or journey, then it will have a certain delay. So although you just increase your gate voltage immediately, but in order to make invariant charge layer, which is used for channel for your transistor, it will take certain time to build up this two-dimensional electron gas. So that represents a certain delay of your calculation result. Okay, so Mr. Jung, are you with me? So that's the simple reason why we have delay. So yes, so that is the reason why we are so much care about the the capacitance when we talk about the RF application of our transistors. Okay. So, Mr. Jung, do you have any further question? Okay. Good. So, of course, up to now, I just explained one most important reason of delay. So delay, the most important reason for delay was the capacitance inside it. Yes, so that's true. But if we go to even higher frequencies, so not like gigahertz range, but if we enter into the terahertz range, then we have additional component which introduce a certain phase difference between input signal and output signal. However, in practical devices, so still we are just in a range of capacitive devices. So I think that it is enough to say that the capacitance is the main reason of your delay observed in this case. Okay, so do you have any further questions? So nice questions from students, and now let's move to lecture our lecture 17. Yes, so we had no lecture on last Thursday due to Children's Day. Yes, Children's Day. Now let's go to lecture 17. If you remember, what we have done in the previous lecture was just to perform transient simulation. So I'm not quite sure you have all done your simulation properly or not, but that is your duty to do the correct transient simulation. So please check your result with some reference simulations. So please do so. Yes, so this is a transient simulation, and in order to make a comparison or verify your result, so I ask you to some analytic approach. So analytic calculation of your y parameter. So we will start from this approach. So in the analytic calculation, what you have done was like this. Yes, in general, we have to consider time varying potential and time varying electron density. However, under the assumption of a small signal approximation, so now we decompose this in general time varying signal into two parts. For example, yes, we just take the DC component, also DC component, which does not depend on the time variable. This is just a constant. And now we introduce small deviation from phi dc and small deviation from n dc. Of course, so I think that we have to disenable this. Okay, so I'm not so sure why it zoom in. Yes, so this is our assumption. Of course, later we will say that this is just harmonic, like sine omega t or cosine omega t. Also, we will assume that this delta n is in a form of a combination or linear combination of sine omega t and cosine omega t. We will assume it later. But anyway, what we have done in the previous lecture was just to assume the form of our solution variables and say that these DC themselves, DC solutions themselves satisfy the semiconductor equation, drift diffusion equation, and now we assert that these delta components like perturbations or small signal responses delta phi and delta n should also satisfy the first order equation derived from the what? Derived from the drift diffusion equations. So that was our previous approach. So do you have any question for our review on the previous lecture? So if you have any question, then please let me know. So our today's topic is small signal analysis, and it is actually just corresponding to the one we have done in analytic calculation. So now think about this case. Usually we have to solve, for example, we have to solve this form, yes, and round n over round t, that is given by this form, and also we have to consider this form. Of course, you know that here in the right hand side terms of these three equations, we have rho j sub n and j sub p. However, they are just functional of what? So n, p, and phi. If n, p, and phi variables are available, then you can immediately calculate this delta, this rho and j sub n and j sub p correctly. So I think that now you can calculate the DC calculation and the AC calculation, no AC calculation, but the transient calculation of your device. Okay. Then I think that let me first assume you have done your DC simulation. So if you have done your DC simulation, then let's call your DC solution as a NDC, PDC, and Phi DC. Then your solution should satisfy this form. Obviously, your DC should satisfy DC. So are you with me? And also in the second case, since you are working on DC, yes, in the DC case, time derivative can be regarded as 0 immediately. So you have 1 over Q, and now you have divergence of your N. However, that is evaluated with your DC solution. And finally, you have 1 over minus Q divergence of JP DC. Yes, this is the case you have to consider. And I assume that you already get the result and think about the boundary condition. So boundary condition, what can be a boundary condition for Poisson equation? Of course, you have two different types of boundaries. One is contact boundary, and the other is non-contact boundary. For example, for contact, yes, now you say that your DC potential is given by what? So let's say that your contact is called as, for example, your contact is labeled as beta, then and your voltage is V beta DC. Then you have V beta DC, and also you have a certain potential. Yes, so you know it, since there is a certain doping usually, so you have a certain electrostatic potential even when the terminal is biased at 0 volt. So this is your condition for contact boundary. And for non-contact boundary, so what you have applied is, okay, your normal component of your electric field should vanish. That was your DC boundary condition for your Poisson equation. Okay, do you have any question? So now let's go to this continuity equation, and I will just show the electron continuity equation only, because the whole contribution also the same. For contact beta, so in this case your electron density, DC electron density, should be N naught. Here N naught is the electron density at equilibrium, so given by your dopant density. For example, if that is anti-Brisson, then your NDC would be very much similar with your donor density. And if that is p-type 1, then actually your whole DC density is very close to the accept density of your p-type region. You know it quite well. And so for non-contact boundary, so non-contact boundary, then you will have this Jn DC term, divergence of this term should, sorry about that. I made mistakes here. Instead of divergence term, I have to say Jn itself, its normal component should vanish. Okay, that was the DC equation and DC boundary condition. So, do you have any question about this small signal? So, preparation of small signal analysis. So, in order to perform the small signal analysis, we first have to perform DC simulation. And DC simulation, you have done it. Although I wrote many things in the right side, however, that has been done by yourself already. Okay, so now let's go to real small signal analysis. In this case, now instead of this NDC, PDC, and phi DC, just like our previous lecture, we will introduce this form NDC and delta n, which is time dependent form. Okay, also PDC and delta P is form. Finally, we will have phi DC and delta phi of T. We will have this form and just put this assumed form of your solution variables into the original equations. And yes, so for example, let's do it together with me about, for example, Poisson equation. By the way, if you have any question, then please interrupt me. So let me just do. Okay, what I wanted to do is, since we have introduced this form phi dc plus delta phi as the phi, so we will have this form divergence of minus epsilon phi dc minus delta phi equal to rho dc plus delta rho. This is exactly the Poisson equation, which is obtained under the assumption of our solution variable. Yes, yes, yes. If this equation is not true, then the blame should be gone to this assumption. Since we have assumed this form, if this form or these forms are not accurate enough, then we will have this problem. However, if this assumed form of our solution variable that is good enough, then we will have a perfectly good equation for our Poisson equation. And now we have certain form like this. What is it? It is just the form we have solved in the DC calculation. So the remaining task is just to make the difference between the overall Poisson equation and DC Poisson equation. If we take the difference, then we can immediately find that this one is gone and this one is gone, because That is the left hand side and right hand side of our DC Poisson equation. So the resultant one is just looks like this, minus epsilon and gradient of delta phi equal to delta rho. Okay, this is the small signal form of the Poisson equation. So from this one, now you can try to also find out small signal form of your your continuity equation. For example, let's try to explicitly write down the form of our electron continuity equation under the small signal analysis. In this case, for example, we have delta round n over round t, but when we insert ndc plus delta n, ndc has no time dependence, so it will become immediately in this form. So let me just write down here, delta n equal to 1 over q, and here we have also something like this. We can consider delta Jn. Okay, so good. But point is, Jn is not a linear functional of our electron and hole, so that is really a non-linear functional. So that makes some problem. So if we have to be more careful about that, then what we have to write down here is like this. If Jn is a functional of our unknown variables like electron density and hole density and potential, then we have to write down in this way: ndc plus delta n, pdc plus delta p, phi dc plus delta phi. First evaluate this full form and just make a subtraction using Jn, which takes ndc, pdc, and phi dc. This difference should be calculated. So let me just do it. For example, Jn, it is given by minus q mu n and gradient of phi plus q dn gradient of n. So now you find that this Jn is actually a functional of n and phi. So let me just evaluate it. When we have ndc plus delta n, yes, now we will have a q n here, ndc plus delta n. Also we have gradient of phi, so phi dc plus delta phi, and plus q dn, but in this diffusion term we have just a linear diffusion, so nothing happens. The drift term makes difficulty. So this is Jn evaluated with ndc plus delta n, phi dc plus delta n. However, Jn, which is evaluated with the DC solution only, then we will have q mu n ndc gradient of phi dc. Yes, we will have this this form. So then let's try to make a difference between this and that. So quite easily, really quite easily, we can find that this term is just cancelled out and this guy survives. And yes, the first drift term can generate 4 different terms. Let me just write down minus q mu n, and we can have ndc gradient of phi dc and ndc gradient of delta phi, delta n gradient of phi dc, and delta n gradient of phi d. Oh, sorry, not phi dc, but delta phi. So this is the drift term calculated with ndc plus delta n, phi dc plus delta phi. So from this term, now we can find the product between ndc and gradient of phi dc. Also, that is immediately found here. So what we can say is, if we just evaluate this form, then delta Jn, which should be appear here, it should be written as like this, minus q mu n and ndc gradient of delta phi. So this is corresponding to the fluctuation of our electric field. And the second term is now considering the fluctuation of our electron density. And finally, we have the term, the fluctuation of both of them, plus this is corresponding to the drift term only. And now I will write down the diffusion related term, and that is written here as q dn gradient of delta n. Yes, this is the form for our delta Jn. But just following our small signal analysis, we always assume that these delta quantities like delta n and delta p and delta phi should be regarded as just a first order quantity, so their product will always generate the second order term, which should be neglected in our calculation. So simply speaking, in the case of our small signal analysis, so this term, which consider both of electron density fluctuation and electric field fluctuation, should not considered in our calculation. So if we adopt this form, then our delta Jn should be given here. So given here means that we don't have this term. Nope. Yes, this is the form we have to keep in mind. Okay. So following the exactly same manner, we can follow the delta Jp. Okay, so I just introduced the AC form, small signal form of the Poisson equation, and small signal form of our electron continuity equation. And although I have not done it, so we have also delta Jp term here. So equations are prepared for our AC analysis. Then how about the potential? Sorry about that. How about the boundary condition? So let's consider the boundary condition. And now we have to consider Poisson equation and continuity equation. First, consider Poisson equation. In the case of Poisson equation, of course, we still have contact boundary and non-contact boundary. And let's say that your terminal is excited terminal. So, for example, gate or anode. In this case, what you have to do is your delta phi at that terminal should be given by amplitude of your excitation, I should be more general in this case. Yes. So in this case you have to excitation, which can be a function of time. Okay, so are you with me? For example, if you apply 1 millivolt amplitude sine, so the signal, then delta phi should be 1 millivolt multiplied by sine omega t or cosine omega t. So this one is shown here, V excitation. Okay, and for other contacts, so for other contact, then your delta phi should be 0. For example, if you are applying the excitation voltage to your gate, then usually your drain is just kept as the DC component, DC voltage. So there is no fluctuation of your potential at that contact region. So you have to select either 0 or either excited voltage. Okay. And how about the non-contact boundary? For non-contact boundary, we have used something like this: gradient of phi, and its normal component should vanish. And now if we insert phi dc and delta phi, of course gradient of phi dc satisfy also vanishing condition for our non-contact boundary. So now it becomes clear that we have to have this form. We have to have this form for our non-contact boundary. So let's go to the electron continuity equation. So same happens to our whole continuity equation, and I will not repeat it. So in the case of electron continuity equation, so we have to satisfy the boundary value of our electron density, and in this case electron density is always 0 regardless the applied voltage at the terminal. At an ideal ohmic contact, we just assume that the electron density follows the equilibrium electron density, so delta n should be 0 at contact nodes. And how about the non-contact nodes? In this case, our delta Jn vector and its normal component should be 0. That is the boundary condition for our our electron continuity equation. Okay, so up to now, I just explained how can we consider the small signal equation and small signal boundary condition. So starting from the original equation, Poisson equation and carrier continuity equations, just to use this form. Yes, this form and this form. Just to assume that your solution contains the DC component and small perturbation, and just to insert it and make a certain calculation and neglect the second order term. Only taking the first order term, you will have the equations and boundary conditions. Yes, that is the small signal analysis. And now if you solve this the set of small signal equations with small signal boundary conditions, and you will get the full information about your delta n, delta p, and delta phi quantities. Okay. So any question? Okay, Mr. Chung. Good. Okay, it's done. Thank you for your feedback. Okay, Mr. Park. Okay, so up to now, the theory is quite easy. It means that, as I just to summarize, the small signal analysis just to assume the pre-existence of this solution, and we provide a small deviation for each solution variable and take the first order equations for our small signal variations. Then you will get the one closed system of equations, and that is enough for you to perform the small signal analysis. Okay. However, the theory itself is so simple and easy to understand, but if I ask you to actually implement it, then maybe that will not be very easy. Okay, so I think that of course I can give you the right direction and just to bring you to there, just to start the correct one. But today is Monday, and usually Monday I do not want to give you much difficult homework problems, because you have to make up your or follow up your previous homework, which is not complete, which has not been done completely. So I just wanted to give you really a simple, uh, really simple homework. So homework 17. So now let me announce homework 17 with 2, 3. Oh, yes. Okay, homework 17. So in homework 17, what I wanted to ask you is like this. You have already done your homework 16. So there you had two terminal device. Yes. And I think that you have already calculate your y parameters from analytic mean and also calculate your delta I as a function of t. So the questions from Mr. Han and Mr. Park was how can we convert it to delta I omega, and how can I make y parameter out of it? So I answered it to you. So now you have sufficient knowledge on this system. So what I wanted to ask you today is just try to implement the small signal analysis in your simulation code. So what is the difference between your previous transient simulation? In your previous transient simulation in homework 16, so you just use your full simulation code. Your full simulation code can be used for arbitrary voltage excitation. However, in homework number 17, instead of considering the full one, just to consider the small signal equations only. Please try to make it and implement it and get the solution and make a comparison between your two solutions, full transient signal solution and small signal analysis solution, and finally the analytic solution. Then you have to have good agreement between all of them. Okay, so in this case you can still work in time domain. Okay, so you don't have to implement the frequency domain analysis simulation. First, just perform your delta n, delta p, and delta phi as a function of time, and after sufficiently long time has passed, then please just to translate your time domain signal into frequency 1, and please try to make a comparison. Okay, so do you have any question? So I will take some questions from your side, and if you don't have any further question, then I will wrap up today's lecture a little early. Okay, I have already covered the important part, but this is not the final contents for our small signal analysis. I just postponed the second part to our Thursday lecture. It is because that will be too much for one lecture hour. So just to consider this first part. Okay. Okay, so good, Mr. Han. So when I say small signal analysis only is previously in your transient simulation, your solution variable was n and phi. But instead of that, now please implement the code heavily, really explicitly dependent on delta n and delta p and delta phi only. Your solution variable should be no longer delta n, should be no longer n p phi. Instead of that, please consider the equation strictly valid for delta n, delta p, and delta phi. Okay, so Mr. Han, so I just explained what I mean using the small signal analysis. Okay, so of course, once again, Mr. Han, this is not the end of our story. So in lecture 18, I will discuss about the better way, more efficient way to implement our small signal analysis. But before directly jumping into this small signal analysis, which is available in the advanced or most of simulation code, but please have your own effort to understand the procedure beneath the small signal analysis. Okay, so so I mean that in this homework number 17, you have to use or you have to perform the transient simulation. That's true. However, in this case, the equation of your analysis or the equations for your simulation is not the Poisson equation itself, the usually used one. Instead of that, please use the small signal Poisson equation. The Poisson equation for delta phi and delta n and delta p. Also, for electron continuity equation, please do not use the general form of electron continuity equation. Instead of that, please use this form. I will write down explicitly. Please use the form looks like this. Please use this explicitly small signal term. Okay. So how about Mr. Han and all other students, Mr. Park and Mr. Jung? Do you have any question on homework number 17? Then please let me know. Otherwise, I will wrap up today's lecture a little earlier. Okay. Okay, good. Then please let me know. So if you have any question, so let's try to wrap up today's lecture. So let's please submit your homework by uh, uh, homework before starting our next lecture, and see you this Thursday. Bye.